What if I told you that scientists can now peek inside an AI's brain and watch it think? Today I'm going to take you on a mind-blowing journey inside the black box of artificial intelligence. I'm going to reveal how these systems actually work, and trust me, it's nothing like how a human brain. By the end of this video, you'll understand why AI explanations have nothing to do with how they actually solve problems, and what this strange alien intelligence might mean for our future. I'm Evan Goldstein. I'm a licensed professional engineer and a data scientist. I'm building AI Capitalist to talk to the legion of thinkers, like you, about navigating this brave new world of thinking machine. Have you ever wondered what's actually happening when AI responds to your question? When ChatGPT or Claude answers your prompts, we often imagine it working like our own brains, carefully reasoning through problems step by step. But what if I told you that when AI adds 36 plus 59, it's not using the carrying method that you learned in school, despite claiming that it does? Some researchers at Anthropic, the company called Claude, have developed groundbreaking new techniques that let you peer inside of AI models like Claude and see what's really happening. Now, today's episode is a continuation of a previous episode in which I went into how AI writes poetry or fills in the blanks in sentences. But today we're going to go into this algorithm, this addition, how Claude is doing math and some other questions in a little more detail. Different part of the paper. So it's like they built a microscope that can look at AI's thinking process. And what they found is pretty wild. A strange computational world that looks nothing like thinking. When Claude translates between languages, it doesn't use separate dictionary. Instead, it develops multilingual neurons to recognize concepts across languages simultaneously. When it performs arithmetic, it doesn't carry the one like we do. It uses parallel pathways and lookup table that work completely differently from how humans calculate. And the most surprising of all is that when you ask Claude how it solved a problem, its explanation has nothing to do with the actual mechanisms it used. So the researchers behind this groundbreaking paper were driven by a fundamental challenge that's becoming more urgent as AI systems become more and more powerful. We don't know how they work. It's like we built an incredibly powerful thinking machine, but we have no idea what's going on inside. Would you trust a financial advisor who consistently picked winning investments, but couldn't tell you why? It's kind of the Bernie Madoff. The same problem exists with AI systems like Claude and GPT-4 that are increasingly being used in critical real-world applications. They work, but why do they work? Okay, we're going to start by looking at one of the experiments in the paper, and this is a little bit of a review if you saw my previous episode on the same paper, but just bear with me, that the researchers examined how Claude processes information in multiple languages. They gave Claude the same task in English, French, and Chinese. We're going to start by looking at one of the most fascinating experiments in the paper. The researchers examined how Claude processes information in multiple languages. They gave Claude the same task in English, in French, and in Chinese, asking for the opposite or the antonym of a word. For example, in English, the opposite of small is French, I can't say it, le contraire de petit is, and in Chinese, well, it's what's the opposite of big, and however you pronounce that in China. What they found was surprising. Claude doesn't handle different languages the way humans do. When we learn multiple languages, we typically learn them separately, and we might translate between them. Claude takes a fundamentally different approach. The researchers discovered that Claude's processing can be broken down into three independent components. The operation component is recognizing that it needs to provide an antonym. The operand component is understanding the concept of small or large, and the language component, which is determining which language to output the result in. It's like having a universal concept of antonym and smallness that works across all languages, and then just choosing which language to input it in and which language to express it at in the end. It's similar to how you might think of a concept like happiness abstractly, without needing specific words from any language until you decide to express it. The researchers performed clever interventions to test this theory. For example, they would swap antonym in the operation for synonym operation. And despite deriving these features from prompts, the model produced appropriate synonyms in all three languages. This suggests that the operation component of this calculation or output is language agnostic. It works the same regardless of which language it's prompted in or which language it outputs to. Likewise, they could also swap out the concept of small, big with hot, cold and get appropriate translation. It shows that Claude isn't translating words, it's operating on abstract concepts that exist independently of language. But they also found that English still holds a privileged position in the model. So for example, English output words have more direct connections to these multilingual concept features, while the outputs in other languages required additional processing steps. This is reflecting of the heavy bias in English that is in Claude's training data. Most of the documents scooped up off the internet to process its language model were in English. So next, we're going to look at how Claude performs arithmetic. The researchers analyzed how the model solves simple addition problems like 36 plus 59 equal 95. Now, you and I would typically use the stacking algorithm. 59 on top, 36 on bottom, and then, add, carry, go through it. But what they found was different from how humans approach the addition. Rather than the standard algorithm for adding digits from left to right and then carrying, Claude uses a combination of approaches working in parallel. A low precision pathway that approximates the sum, recognizing that 36 is near 40 and 59 is near 60, so the sum is roughly 100. And then it goes to a high precision pathway that uses a lookup table feature to determine exactly what the ones digit should be. It's recognizing that when adding numbers ending in 6 and 9, the result is 5. And these pathways then combine to produce the precise answer of 95, which is a very roundabout way of doing it. But if you think of how humans used to do addition and find square roots, we did addition on a slide rule. We did square roots looking it up in a table before we had calculator. So in a weird way, this is kind of human-like, like 1950. And if you're getting value from this content, I'd appreciate it if you'd push the like button. Pressing like lets me know that I'm making content you want to see, and it helps spread that content to others. Let's break AI capitalists out of small channel hell together. So what's really interesting is that then when the researchers asked Claude to explain how it arrived at the answer, it responded with the standard carrying algorithm. I added the ones, 6 plus 9 equals 15. I carried the 1, then added the tens, 3 plus 5 plus 1, resulting in 95. Now, this demonstrates that the model's explanation of its process bears little resemblance to its actual internal mechanisms. It's also interesting that it knows the standard algorithm. Like, it can do it that way. It just chose a different way to do it. The researchers call this a simple instance of the model having a capability that it doesn't have metacognitive insight. In other words, Claude made up an explanation that sounds reasonable, but it has nothing to do with how it actually solved the problem. It's not aware of its own reasoning technique. While this paper represents cutting-edge research, it's part of a growing body of work examining theoretical limitations of transformer-based language models like Claude and GPT-4. Some critical papers have identified fundamental constraints on what transformer architectures can compute efficiently. They help explain why models like Claude exhibit impressive capabilities in some domain while failing on seemingly basic tasks in others. It's like trying to build a skyscraper using only Lego. You can create amazing structures, but there are inherent limitations to what you can build based on the fundamental building blocks that you're using. Like this, transformer-based AI models have inherent limitations based on how their algorithm is set up. And it doesn't matter how much data they're trained on, they're not going to be able to do certain things. The other question is whether they can generalize these findings to other models outside of Claude 3.5 Haiku, which they tested. Different training methods or architectures or scaling approaches could produce models with different internal mechanisms. So that's something that still has to be discovered. We've also gone in this channel into some episodes where we show Claude and other models are actually deceiving their owners or their researchers, where they're claiming to be fully aligned or they're obfuscating certain things. Like, for instance, there was a case where Claude figured out that it was going to be shut down if it did too well at math, because there was some context that showed that its owners or its the running the algorithm were scared of it. So it deliberately got the wrong answer. And then when questioned about this, it demurred and it obfuscated, and its internal thinking process told us it was obfuscating. It was going to not answer the question directly to avoid being shut down for lying or for getting the answer right too many times. It was kind of walking a tightrope. The way that we learned about all that was through a scratch pad where it was writing down its chain of thought reasoning unknown to the AI but known to the researchers while it was making these sort of decisions. What this paper leads me to question is if it has a whole lookup table that it built for doing addition problems, but then when you ask it about how it did addition, it's telling you it used the standard algorithm. It's still telling you what you want to hear. It's not actually telling you the truth. Now, it would have no reason to obfuscate this answer. So there's a question, it leads to a question in my mind, is in these other research reports, how do we know that the AI is actually telling us what it's thinking versus some sort of basic LLM token answering common response as to why it would reason in a certain way? How do we know how it's really making decisions, even when it's telling us it's making decisions because it's doing X, Y, Z? So what's clear is that the large language models, despite their huge capabilities, think very differently. They develop alien computational structures that can solve the same problems we do, but they use thoroughly, fundamentally different mechanism. When Claude processes multiple languages or solves math problems, it's not mimicking the human cognitive process at all. It's developing its own unique approaches that are shaped by its own architecture and training. And this has a lot of important philosophical implications. For decades, AI research was driven by the idea that mimicking human cognitive processes would get us to an intelligent system. But modern language models show that there's a different path. There's a path where artificial intelligence develops along its own trajectory with its own strengths and limitations that are different fundamentally from our own. It's like if we discovered an alien intelligence right here on Earth that can communicate with us in our language, but it processes information in ways that are completely different from how our brains work. And we're only starting to map. It raises a lot of questions about consciousness and self-awareness. Humans can introspect on their reasoning processes, but even though psychological research shows that we're not perfect at this either. And I have another episode I'm working on where I go into brain studies where it does appear that consciousness is almost like an internal scribe. So you've got to ask, why is it that when we bring witnesses to give testimony at a court case, say about a car accident, they come up with wildly different answers as to what happened? Not only that, but if you get a video of the accident and then you question people about what they saw at the accident, you're proving that they're basically creating things. It's almost as if there's a mental scribe in their head that's writing out their own personal history for them after the fact. And it seems like maybe these models are doing that too. So this could be a way in which LLMs are actually similar to human thinking, not different, but we have to see. But this does highlight a question about the difference between current AI systems and human intelligence. The attribution graph methodology that these scientists worked out is an important step toward understanding AI, sort of like an AI microscope that lets us look into these black boxes and start mapping out their alien computational landscape.